All right, so for today, let's pick up where we left off yesterday. We were in the middle of section 421, and we have some rational functions here. Page 35 does not have any equations given to you. They're all transformations of the equation y equals 1 over x. So if you would copy these down, top of the page, y equals 1 over x plus 2 minus 1, and y equals 1 over x minus 3 plus 4. For each of these, you're going to give the transformations as it appears here in this example, and then give a graph of it. So drawing your asymptotes with dotted lines, and then plot a couple points in the quadrants, the newly established quadrants from the asymptotes that show the curves that would develop from these hyperbolas. The one at the bottom of the page is going to be y equals negative 1 times 1 over x plus 3 plus 2. So now we have a stretch factor in front with a negative, so remember what that does to the graph based on the Desmos exploration that you did in the previous lesson. You also can then work on these five problems here, either taking a shift and writing an equation or taking an equation and writing the shifts. All right, so you can pause and work on that for a bit and then come on back. Okay, for those that worked on the homework assignment for last night, let's go through these just for a minute. So numbers 1 to 3, you're taking the info given and writing the appropriate equation. For numbers 4 through 6, you're taking the equation and explaining what is happening. Note the compression when you have a value between 0 and 1 before the fraction, and a stretch when you are bigger than 1. For 7 and 8, you should have drawn in the horizontal and vertical asymptotes and then name them. Each k point is just going to be the intersection of those asymptotes. So x2, y1, domain then excludes those values, and then the equation would have to show that shifting. And finally, some radical practice. So taking each one, breaking it into a square factor, and then simplifying from there. Okay, so for the first set of notes for today, actually we're going to come back to 43 in just a minute. This is on page 38. So we've got 8 graphs on pages 38 and 39, and I just want to take you through each one. 8 different functions that we have looked at so far, or at least should know something about. So we'll start off with x squared. This one will take us the least amount of time because we've already explored this one pretty comprehensively. You have your table going the 1, 4, 9. I didn't show the 9 in this table, but we know that it's going to start at the origin and work its way up on both sides with symmetry, and the general equation we've seen many, many times. So we have that set up. Now, the reason I start with this one is because the structure for all of our functions is going to be very similar, where we have a stretch factor in front, we have an h value tied up with the x as a horizontal adjustment, and we have a k value that is at the end of the function as a vertical adjustment. So the same thing is going to occur when we look at y equals x cubed. So the difference to start with a cube and a square is that we don't have that symmetry across the y-axis now, because if we use a negative number in a cube, we get a negative output. So those values are going to continue decreasing as x gets lower. And as x gets higher, we do increase, just at a faster pace. So it kind of looks like an S shape. It's got a little waggle to it in the middle. We're going to have a locator point in the center of these graphs where it flattens out, and that is going to be at the origin unless we have any shifting. So the shifting would work the same way as a quadratic. Feel free to add any additional notes that you hear verbally here if anything sticks out to you as something that might help you out. The h and the k are in the same positions, the a is in the same position, so all the adjustments work the same way. And the h and the k would just move this center locator point around. But we would still be 1 away in each case from the original point, and then 8 away, unless we have an a value, and then that would multiply the distances from the origin point, just like it did with a parabola. All right, square root graphs. Square root graphs basically take a parabola and put it on its side. So now I've got my square numbers as my input because my intent is to square root them and do so in an easy way. So I set up perfect squares for my start points, my start inputs, and I get square roots for my outputs. Starting at 0, 0, and it goes up and away at a slower pace. All right, that's the basic shape of a square root graph. When I shift it horizontally, this start point at 0, 0 would move along the x-axis. So if I had x minus 2, then I would use x equals 2 to create a 0 as my start point, so it would move over to the right. The k value is going to shift it vertically like it always does, and so we would see this starting point shifting around the grid based on what h and k are. The a value does the same thing as it does with a parabola. It stretches it out away from the origin. So if you can follow my cursor here, an a value bigger than 1 would well, let's actually explore it a little bit. Let's say that I had 2 times the square root of x, then all of these values would get doubled, because I would do the square root first, and then I would double the result. So if I doubled all these values, I'd still have 0, I'd have 2, I'd have 4, I'd have 6. So these values would be twice as high, pulling them away from the x-axis. So it's stretching it out. And if I used a value between 0 and 1, it would pull it toward the x-axis. All right, so the curve itself, it looks like it would get wider if I pulled it away, but remember it's in relation to the x-axis, so it's stretching it vertically when I have a value greater than 1 for a. All right, so cube roots do the same thing. I've got my locator point in the center. This time I've got my cube numbers as my input because my intent is to cube root them. And so those cube roots are in the right column. And the structure of this is exactly the same as it was for the square root function. You need to know the shapes of these. So when you see this flat looking S shape, that should be a clue to you that it's a cube root graph. If you see the half parabola on its side, you know that it's a square root graph. Probably something worth making flashcards for, where you have a basic graph shape on one side and a parent equation followed by a general equation on the back side. Be a really good way to quiz yourself. So the h and the k would move this center point just like it did for the cube graph, and if I had an a value bigger than 1, it would stretch it away from the x-axis in both directions, and if it was less than 1 or between 0 and 1, then it would make it closer to the x-axis. Okay, if you had any concerns on those 4 functions, they should be written down by now and be ready to address those in the next lesson. All right, on page 39, so we addressed this function, this hyperbola reciprocal function, last time. I've got my table showing that when I have a fraction as my input, I get a whole number as my output, and vice versa. I cannot use 0 for either the input or the output, therefore asymptotes at zeros. If I make a horizontal adjustment, it will be with the x as always. So since the x is located in the denominator, my horizontal movement is in the denominator. And vertical movement is always after the fact at the end of the function. Still is here after the fraction. Stretch factor would normally be in front. I have moved it into the numerator because that's typically where you see it located. But multiplying a number in front of a fraction is the same as using it in its numerator. So it has the same exact effect. Asymptotes occur at the horizontal shift and at the vertical shift. So this graph would normally originate at the origin, but if I have a k value, it would originate higher or lower. And if I had an h value, it would originate further right or further left, establishing essentially new quadrants for these branches to approach. All right, we have dealt with exponential functions in previous units. So I've got one example where the base is more than 1, and one example where the base is between 0 and 1. The only difference between those is the direction of the curve. So it's heading up and away in this case, and it's heading down toward in this case, but we've been through that before. All right, so in the shifting version, since my horizontal shift has to occur where the x is, that would be in the exponent, and any vertical shift would occur after the function's over, so at the end. This horizontal asymptote occurs at 0 on a graph like this, but if I shift it up or down, the k value is going to dictate where that asymptote goes. So if I had a +4 at the end, my asymptote would be written at 4. And if you follow my cursor here, this is where it would be. All of the graph then would live above that line. All right? And if I have an h value, then this first point at 0, 1 would occur a couple steps to the right or a couple steps to the left. An a value is going to make it steeper or flatter, and it's going to basically have the same effect as changing the base, but it is its own thing. And if I have a negative a value, it'll have, so let's say I had a -1 times 2 to the x, -1 times this whole thing, then every single y value would become negative, and the graph would follow the same curve below the line. If I go -2, then it would be a steeper curve below the line. +2 would be a steeper curve above the line. So a stretch factor in front is going to pull it away from the x-axis. And a stretch factor between 0 and 1 would pull it closer to the x-axis and make it flatter, no matter what side it was on. All right. The assumption here is that b is greater than 1. So all graphs with a base greater than 1 are going to behave this way. If the graph has a base less than 1, all the same things happen. I have an asymptote at 0 unless it's been shifted, and I have an h value with the x and a k value at the end. If I have an a value less than 0 here, so in other words a negative a value, then the graph would do the mirror image. It would still approach the x-axis because of the fact the base is less than 1, but it would approach it from the negative side. All right, and if I had an a value greater than 1, then everything would be steeper. If I had an a value between 0 and 1, it would be flatter. Finally, absolute value. This is a new one. So with absolute value graphs, we know that if you use a negative number within an absolute value symbol, it becomes positive. So all of these negative inputs would create positive outputs, and therefore it creates its own symmetry like a parabola does. It's just that there's no squaring. So it's like a linear function on one side. It has a slope. If there's an a value in front, it would have a slope to it. But the mirror image is on the other side of that vertex. The vertex is going to be wherever h and k says it is. So normally at the origin, but could be shifted around just like in a parabola. And a negative a value would just make the v shape open upside down. So those are the 8 basic functions that we have at this point. We will have more throughout the course of the year, but that's what we have to this point, and those are the ones that you're responsible for at this time. Again, highly recommend flashcards with a graph on one side and a parent function and general equation on the other. All right, let's wrap this up with some notes on page 43. All right, so generalizing. This mentions something about a parent graph toolkit, and there is one of those at the back of your packet, which might be useful for practice, but I just went through all the different function types that we will need, so you'll use pages 38 and 39 if you need to reference. So the first step to graphing a shifted parent function is to determine what parent function it is. So you have an elaborate equation in front of you. You have to break it down to its bare bones and say, all right, that's an x squared equation. It's going to be a parabola just with some shifting. Or it's going to be an x cubed type of s shape. Or maybe it's a root or a reciprocal function. Whatever it is, you need to figure out where it comes from. Then you're going to figure out how it's shifted, figuring out where h and k are. Plot your locator point, which might be the intersection of asymptotes, or it might be a vertex, or it might be a flattening point, or a starting point in a square root graph. Whatever it is, plot that first. Item 3 here, determine the stretch factor. You're looking in front of the function for that, and if it's bigger than 1, you're going to have to multiply. If it's between 0 and 1, you would also have to multiply. And if it's negative, you'll keep in mind that it'll flip over. So you'll use the parent graph table to help you plot the points for the graph. So you can make a parent graph table for these and then make adjustments off of that shifting. Or you can just make those adjustments directly on a graph. Finally, you check your work and make sure your graph is the right shape. So let's look at a couple of examples of this. My first one here is clearly a square root graph. And so I've written my parent function without any of the shifting. And then I'm thinking normally that would start at 0, 0. But this is shifted 1 to the right, so I'm moving over 1 unit. And it's shifted up 5, so my first point goes here. I've also made a sketch of the shape over here to remind me how it should look when it's done. And from there, I can use my concepts of square roots, knowing that when I move over 1 unit, I'll be up 1. Over 4 units is square root 2, so I'd go up 2 units. And then over 9 units would be square root 3, so I'm up 3 units. So since there's no a value in front, nothing's been stretched, and I'm using that 1, 4, 9 concept going horizontally. There is no stretch factor, and the domain is going to start at this first HK point, and it's going to start there for the range as well, including those points with brackets off to infinity in both the up direction and the right direction. Item number 2 is like an exponential. It's got a vertical shift of -3, but otherwise it's going to behave like 2 to the x power, which would normally go through 0, 1, and then up and away. So because it's shifted down 3, the asymptote is now at -3 instead of 0. And the first point is no longer at 0, 1, it's at 0, -2. Every point is shifted down 3 units. So from the first point, I know that if I double it, I'm going to be 2 above the asymptote. And then if I double it again, I'm going to be 4 above the asymptote. So that's how I'm plotting my points. You are always permitted to make a table if it's easier, but I definitely recommend that you try to see patterns because it does make the graphing faster and simpler. All right, there is no stretch factor in front of this. Be careful with that because the 2 kind of looks like a stretch factor, but remember that's the base of the function. That is not a stretch factor because it is not being multiplied in front. So there is no stretch factor to this. Domain is infinite, so you can write it with an interval or with the all real number symbol. The range starts at -3 and goes to infinity, but we're not including -3 because that is an asymptote. So we need to show that with parentheses in the interval format. All right, last example here is the rational function or reciprocal function. I'm noticing x on the bottom, so I'm thinking of it as if there was no shifting, would be 1 over x. That's this shape, first quadrant, third quadrant. But this shift is left 3, so my vertical asymptote is at -3. This shift is up 2, so horizontal asymptote at 2. And then I can have my points on there. Now, what I know about a reciprocal graph is that there's always a point at 1, 1, and there's always a point at -1, -1. So unless I have a stretch in front or in the numerator, my first point in each direction should be 1 away from that intersection of asymptotes. And then from there, you can just make your normal curves. There's no negative in front, so I know it's going to be in this first quadrant, third quadrant pattern, and just make it approach both lines without crossing over. Domain is going to be based on your vertical asymptote and range based on your horizontal asymptote. All right, so at this point you can work on pages 44 and 46. If there's still time in class, those are a homework assignment. If not, answer keys have been posted on Google Classroom. Just refer back to these examples for any help in those problems.